species. Never knew that. They had to just. They need to do a civil through two parts instead of an AutoCAD. AutoCAD's all draw. And let's see, but still we need as a service is more, you know, 5 hours. Like it's AutoCAD. Everything is AutoCAD. Like once you have that works is underneath. Yeah, it's difficult, but it's sick. Yeah, they were gonna be I like that. Yeah. And you don't have to get trained to be like a company. I haven't gotten, and I know a lot of they're AutoCAD. Obviously, it's like I wanted to know. I know you have AutoCAD training, but I've tried to fit in the past. So you could definitely workouts.
So really, like, switch to so like watching my TV, you just go like this all.
Control.
Yeah. So like instead of getting inside for a minute for like F1, but some press the it goes like a certain inside. Yeah, and we're just press the first letter F. That's why it's
Yeah, what the other things heaped up that 4 days between worlds. Life.
So we didn't have to watch it.
Right. I was pretty sure. Totally.
No, next week is already close. The next last was already.
It's the 60th. Do you know which one's first? Jaws novels first. There's a other one where I'm sure you're not. It's like conductivity, and then the border.
I got them fixed. I need something. Well, like harder over. Yeah, no, I got tires.
But next one's like, look a little bit. You can do things up so. If you group 5, that's 4, 5. Okay, 4. I think it's 4. So it's 75. Yeah, it's a year. It's a year, 2 weeks. It wasn't one.
Okay, folks, let's get started. So we left off last time looking at hydraulic conductivity, and I wanted to show an example where we have a block that has 2 layers in it. So one layer is 1 meter thick, and another layer is a centimeter thick. And I drew the second layer in the middle of the 2 layer, but really, we can think of it like 1 layer here and maybe another layer here. It's easier to visualize with a layer in the middle, but really it's just 2 layers of different thicknesses. So layer number 1, the thick layer, has a hydraulic conductivity of 10 to the minus 4 meters per second. So that's the sand. And then layer number 2 is 10 to the minus 8. So that's a silty clay. And there's the thicknesses. So just the thin layer of silty clay. And so what we want to do is say we've got this situations block with 2 layers in it, and we want to go and have an equivalent block that's homogeneous, there's no layers, it's just anisotropic with a hydraulic conductivity horizontally parallel to the layer and perpendicular to the layer. And intuitively, I think I'm drawing this one longer than this one, because I think intuitively we think of the effective hydraulic conductivity as a resistance to flow. There's going to be less resistance in this direction because the flow can just go through the sand. But if it goes through this in this way, it's got to go through that thin clay layer. So there's going to be more resistance that way. Just intuitively, that's how it seemed like it ought to work. And so what we said last time was that the effective or K horizontal parallel layers effective was well, I think it was like 1 over BT times K1 B1 plus K2 B2. Okay, so we can substitute in BT. I guess BT is going to be 1 plus O1. So it's that. Essentially, it's just going to be 1. And then K1 is 10 to the minus 4 times B1, which is just 1. And K2 is 10 to the minus 8. And B2 is 10 to the minus 2. Okay, and both of this would be meters per second, and this is meters per second, meters. Okay, so that's what we have to do. And we can go and put it in our calculator, but just to save a little bit of time, we can just say, okay, we're adding this and this. So this here is 10 to the minus 4. Okay, that's 10 to the minus 10. If you add 10 to the minus 10 to 10 to the minus 4, it still is going to be 10 to the minus 4 pretty much. Right? I mean, it'll have a little bit on it, but it doesn't matter. So we could just say that for our purposes here, we can just ignore that. Okay, so the effective horizontal conductivity for this case is essentially the same as the highest hydraulic conductivity. Okay, and we kind of thought that intuitively, but here it falls out of this average. Okay, so we can do something similar for vertical. So K vertical effective, and this was the harmonic average, so it's this B1, B2, K2. Okay, so that's 1.01 meters. Okay, so substitute it in. There's 1 meter, 10 to the minus 4 meters, and then this is 10 to the minus 2 over 10 to the minus 8. Okay, so what's going to happen then is this is just going to be that, and 1 over 10 to the minus 4 is 10 to the 4th, right? So we get that. And this is so 1 over 10 to the 8th, 1 over 10 to the minus 8 is 10 to the 8th. Multiply by 10 to the minus 2, that's 10 to the 6th. Right? So okay, so 10 to the 4th plus 10 to the 6th. So this is 10,000 and that's a million. I mean, it's essentially just a million, essentially, right? And so this is gonna be, I think it actually works out. I think you add this and it cancels with that 0.01. So this ends up being 10⁻⁶ meters per second. Okay, so we got an anisotropic condition here. That's 10⁻⁴, and that's 10⁻⁶. So it's 100 times more hydraulic activity, effective hydraulic activity, 100 times greater horizontally than vertical, as a result of having this clay layer here. So the way these averaging formulas work, these are two different styles of averaging. This one is dominated by the highest value here. This one is controlled by the lowest, right? Because you would see that this one, this ends up being greater than that. Okay, so it's not as low. This isn't as low as the lowest, but it's just a thin layer, right? So this is really just 1% of the overall. So the effective vertical is about 1% of that. Okay, so that's how it works. A lot of aquifers consist of horizontal layers. So they are typically going to be anisotropic, where the conductivity horizontally is greater than vertical. Okay, so we're in the midst of learning about important properties that we're going to need to know to analyze flow through aquifers. So we've just finished looking at hydraulic conductivity and transmissivity. So those are properties governing the transmission of flow through aquifers. The other class of properties is storage properties. So remember from our balance, our water balance, we had flows going in as flows going out, plus the change of storage within the control volume. So we need to take a look at how that works and how to describe the storage process. So these are the storage terms that we need to understand the properties: specific storage, storativity, and specific yield. So we'll learn about the processes that go on and how these are defined. Oh, okay. So here's a reminder that I had here in the slide deck for your upcoming homework. One path line starts at any particular point. This is probably the biggest thing that people do wrong with doing flow lines. Be upstream for gaining streams, and make sure your contour lines don't cross lakes. And gradients. Okay. All right. So specific storage and storativity. So what we need to do is understand how water is going to be removed from storage in an aquifer and added. Okay, so there are going to be a couple of different mechanisms. So in an unconfined aquifer, I think it's pretty straightforward. If you have an unconfined aquifer, may I use this? Yes. Okay. So here's your unconfined aquifer. We take the water bottle and we fill it with sand, and then there's water in the pores of the sand. And in order to get the water out of here, we would hole in it conceptually, and then the water would come out, and the mechanism would be draining of the pores, right? We would drain water out of the pores. The water was stored in the pores, and we would drain it out by gravity. Okay, so that's a mechanism of release of water from storage in an unconfined aquifer. Okay? So maybe it seems obvious, but we're gonna need to identify these different mechanisms to make sure that we're doing this correctly. Okay, so unconfined aquifer, this is typically what I've been drawing. And when the water table drops, the water drains out of those pores, and that's released from storage. Now, we also have another kind of aquifer, that's a confined aquifer. And conceptually, what's going on here is there's a layer right here, that's the aquifer confining layer. And the concept is that there's no flow going across this layer. Okay, so we pump water, water comes out, and since there's no flow, and the water table's up here, the water table isn't really affected when we pump water out of the confined aquifer, right? So there's no flow here. So there are no pores to drain. But yet when we pump water out, we got water come out. I mean, aquifers could also be an oil reservoir. You know, I mean, you go down an oil reservoir, you're a few miles down, start pumping, the water table isn't going to do anything. You're not going to be draining out pores. But yet you can get fluids to come out. So what's the mechanism? It's not pore drainage. What's the mechanism?
Storage. Is it storage?
Well, it is, it's water is being removed from storage.
Okay.
So
Pressure.
in both cases, this unconfined is pore drainage. So we need another mechanism for how the water gets removed from the aquifer.
Is it the pressure of the overhead rocket material kind of pushing down on the impermeable layer to like force the water out?
Kinda, yeah, kinda. Let's do another experiment here. So we take this water bottle and we fill it with sand and we fill it up completely to the top with water. Okay, so can we get water to come out? How?
Maybe with a well.
Put a well in, yeah, but what's the mechanism that you can get to have the water? So you would, let's say you would, well, it's filled up completely, and you're not allowed to drain can't put any air in there. You're not allowed to drain the pores. So how would you get water to come out? Kind of like the overburden pushing down. I mean,
Like pumping from a well.
yeah, but what does that do? What does that do in here?
Makes sense.
Vacuum, okay, or I mean, changes the pressure. What is that going to do? How's water get released?
So if you
change
change the pressure in the aquifer and make it flow from, or heightens the pressure in the aquifer, it makes it flow from high head to low head.
You drop the pressure. If you pump, you're going to drop the pressure in the aquifer. Yep. So what does that do? Why would you get water out if you drop the pressure?
So compacting the materials, compaction.
So if you drop the pressure of the water, then the water's holding the aquifer, the water's giving support to the aquifer, right? The water pressure is partially supporting the overburden. So if you drop the pressure, then it's the support that the water pressure was doing is reduced, and the water and the aquifer gets compressed. I think of what you're going at. So you can, one way you can get water out of here, if it's completely filled, is to squeeze it, compress the whole bottle. So you would change the volume of the bottle. That would, you would have water squirting out, right? Okay, so that's one way to do it. What about if you had it filled with air? So I wanted to, if it's filled with air instead of water, and I wanted to get more air in there, store more air in here, how could I do it with air? Well, you could just pump it in there, right? You could put more, if it's just filled with air under atmospheric pressure, you get more air in there if you hook up the air compressor, inject more air, and that causes the pressure to go up. So there's more air in there though, right? More air in, and the consequence is the pressure goes up. So how do you increase the storage of air in here by increasing the pressure? What's the property of the air that allows you to do that?
Compressibility.
Yeah, it's compressibility. So air is compressible, and if we change the pressure, if we increase the pressure, we can get more air in here without changing the volume of the bottle. If we drop the pressure, then we can get air to come out, right? So I think somebody said put a vacuum on it. Yeah, if you drop the pressure, then fluids expand and come out if this volume doesn't change. So could we do that with water? If it was filled with water, could we get more water to go in there? No. Why? Okay. Is that true? Is water not compressible?
I think like it is, but it's just like hard to do.
Okay, yeah. So is it, if it's not compressible, that means the compressibility is, but if it's slightly compressible, then it's not zero, but it's small. But if it's small, that means that if I wanted to get more water in here by increasing the pressure, I could do it. Not a whole lot, but a small amount. If I wanted to get water to come out, I could do it by dropping the pressure because the water is going to expand. Now, I mean, I couldn't get much to go in or out of this water bottle, but what if I had an aquifer that was like, miles across and 100 feet thick? If I change the pressure there, drop the pressure, the water's going to expand, and that'll be water coming out. Okay, so that's the compressibility of water. And then also we recognize that the aquifer itself is compressible. So when we put a well in an aquifer, we pump it, we drop the pressure. That does two things. It shrinks the aquifer and it expands the fluid. That's how we get water out of the ground in a confined aquifer. That's how you get water out of a oil well or oil out of an oil well, from the compressibility. And it's both the compressibility of the aquifer, the solid material, and the compressibility of the fluid itself. Okay, so here's my little animations. So here's the animation for removing water from storage in a confined aquifer. So the water table drops and you have water come out like that. And then here it is for a confined aquifer. So you drop the pressure by that much. We haven't drained, this is the aquifer. We haven't drained anything in the aquifer, but because we dropped the pressure, the compressibility causes the water to expand and aquifer to shrink. Okay, so these are the two mechanisms: drainage of pore space and decompression of the pore space in the water. Okay, so I need to define a term here. This will be storativity, and it's the volume of water released from storage per area of the aquifer per unit of head drop. So I'll write it like this: storativity, capital S, volume of water released from storage per area of the aquifer per drop in head. Okay, so here's my little plug of aquifer material, and I'm going to drop the head from here to here. There's the cross-sectional, or there's the area that I'm talking about, that area, that's the delta H, and then we'll get that much water come out. Okay, so this will depend on how thick the aquifer is. This is like a plug down through the aquifer. So here I can go some arrows here. So so we drop it, there's delta H. And that's the area. And then the water that comes out, that's delta volume of water released from storage. Okay, so in an unconfined aquifer, the volume released from storage per call it. Okay, so that's storativity. But in a unconfined aquifer, if we here's the aquifer, and if we drop the head from here to here, drop the water table from here to here, then that's A. So draw this a little bit better here. Okay, so here's the area. We drop the head from here to here, drop the water table from here to here, and then we have a volume released from storage. And that is then the volume. Basically what's happening is this is the volume that drains out by gravity. So we can also call this the volume that drains by gravity per total volume to basically total volume drain. So this is the volume that gets drained. So this is called the specific yield. The volume released from storage per volume drained by gravity. Okay, so the specific yield is essentially the same as the storativity for an unconfined aquifer. So for a confined aquifer, what we'll see is that storativity depends on B is the water compressibility, and N is porosity. alpha is aquifer compressibility. And this is the unit weight. Okay, so beta, the way compressibility is defined, it's the volume change per total volume per change in pressure. Okay, so this is going to be the volume change per total volume per change in pressure. Okay, so the compressibility of water is about 1 part per million per, well, think of this as a fractional volume change per change in pressure. Okay, so water would undergo some fractional volume change per change of pressure in PSI. Okay. So that's this, and we can also write it, the aquifer compressibility that way, as volume, change of volume, total volume, change of pressure. So the beta is change of volume, total change of pressure. The unit weight, though, it's basically a pressure per length. Okay, so that cancels with that, and it gives you the change in volume per total volume per length. Okay, so when you see storativity written like this, it's the, you think of this as the change of volume per total volume per change in head. And actually, this should be specific storage. This is not yet the storativity, this is the specific storage. Okay? And then we'll multiply this times the thickness. Well, so the storativity is the specific storage times the thickness. Okay, so this thing here, this is the property of the material. It's partially the compressibility of the aquifer. That's the compressibility of water. That's porosity. So that's like how much the water is contributing to the compressibility. And that's the compressibility of the aquifer skeleton. Okay, so this is a material property. And we multiply by thickness to give the storativity, the storage of the layer itself. Okay, so you see this specific storage written, sometimes you see it like that. So it's units of 1 over pressure. Sometimes it's like that, it's 1 over pressure head. So that's why I have it written with a prime or with no prime. Usually, yeah, usually it's per change in pressure head. Okay, so specific yield is equivalent to storativity. Specific storage times the thickness is the storativity for a confined object. Okay, so this compressibility stuff, I want to show you in a little more detail how that works. And for that, we're going to need to take a look at the how aquifers are forming in response to a change in pressure. Okay, so we've got porous material here, and the arrow here is the weight of the overburden. So that weight is supported by fluid pressure, those little arrows there, and the stress on the solid material. So the total, this is the total load from the overload. And that's gonna be supported by the stress on the solids, which we'll call the effective stress, and the pressure. Okay, so those two will be working together. The pressure, we can write that. We can write that using the hydraulic head. So that'll be oh, sorry. H. Okay, now let's say that we change the total stress. Okay, so we pile a bunch of soil on here. We build something heavy. Okay, that's going to cause a change in the effective stress and a change. It could cause either one of these to change. Okay, but now let's say that the change in the total stress is 0. So we don't build anything up here. It just stays the same, the total stress. Nothing's happening here. Stuff's happening here, but nothing's happening here. Okay, so I guess we've got a confined aquifer, and all the stuff above the confining layer just is hanging there, not doing anything. So this is 0. So if this is 0, then this must equal minus that. Right? So if that's the case, then the change in the effective stress must equal minus change in the hydraulic head. Okay, so now I want to go back to the definition of storativity. So that's the volume released from storage per area so it's per area per, remember what this was per drop-in head. Okay, so this delta H is negative. So if we define delta H, well, this delta H is negative, but by the way we've defined specific storage, we don't want this to be negative. What happens is the volume gets released from storage when the head drops. Okay, but we've defined a drop-in head as being now positive. So this thing ends up being positive. See how that works? The delta H, we switch the sign so that this thing becomes positive. Okay, so within that context, we have, this text. If we assume that the delta H, the drop-in head is up. Okay, so here's what this says. This says if the head drops, then the load on the solids increases. Okay, this is the load on the solid grains, pushing those grains together. So basically, what happens is if you drop the head here, you're supporting the total stress less. That shifts more of the support onto the grains here, and the grains deform. So this, if that increases, that causes the grains to deform and compress together. So we said that the change in storage was gonna be from the aquifer, from the water expanding and the aquifer contracting. This is the aquifer, well, the change in stress like this will cause the aquifer to compress. Okay. So I'll show you how that all works. Okay, so here's the definition of water compressibility. If the change in volume of water per volume of water per change in pressure. Okay, so, and we have a minus sign in there because we want to make sure that this ends up being positive. So we can say that the volume of water inside of our block is equal to the total volume. Guess what we've got here is here's a little block with total volume VP. So the volume of water that's in there is N times V. N is the porosity. And yeah, this is on your handout too, so. And then the change of pressure is equal to the gamma times delta H. And I've got rid of the minus sign because now this is a drop in head. Okay, so this, I'm gonna write this now as the change of volume of water stored from, I'm gonna put a little beta in there because this is from aquifer compressibility. And it's, I'm gonna basically solve for that. And it's beta times this stuff. Okay, so let's move this block here. So here's the aquifer compressibility. And we're going to find it in the same way as the water compressibility. It's the change in the volume of the aquifer per total volume per change in effective stress. So the effective stress, changing the effective stress is what changes the causes the aquifer material to deform. Okay. So then we said on the previous slide that the change in the effective stress we could write as the gamma delta H. So if the only way we change the effective stress is by changing the fluid pressure or the hydraulic head, then we get to make that substitution there. Okay. All right. Well, what we've done here, this is our aquifer here. And if we change the effective stress, then we change the volume of the aquifer. And if the aquifer consists of water and solid grains, if we assume that we can't change the volume of the solid grains themselves, the actual like round grains, then changing the volume of the aquifer, we reduce the volume of the aquifer, then we're gonna increase the water volume that has been released from storage. So change of the volume of the aquifer equals the change in the volume of water that's released from storage in the aquifer. And the minus sign goes away because as the aquifer shrinks, the volume of water that's released increases. See that? Okay, so the change of the volume of water that's released from the aquifer, that is equal to the compressibility of the aquifer. BP. Okay. So the total volume released from storage from this due to aquifer, water compressibility, aquifer compressibility, it's this plus that. Just those two contributions. So that's going to be so I'm gonna, I have some common terms here. So I'm gonna factor out VT. Factor out delta H. So the volume released from storage per total volume per change in head is equal to that. Beta, that's porosity, compressibility of water, compressibility of aquifer, unit weight. So we said a couple slides ago, this is called the specific storage. Okay, it has units of, there's volume, length, that has units of 1 over length. So we could write this. How about if we, let's do it like this. So here's the aquifer. Here's the confining unit. So let's take a plug through there. Okay, so there's the plug. So this is VT. So VT is the thickness times the area. So we could say that's the volume, total volume released from storage. VT is V times A delta H. Okay, so that's another way to think about the specific storage. If we multiply that times B, so let's call it SS. So SS times B, the B's cancel. You get the volume released from storage per area per drop in head. We said back at the beginning was this was the storativity. Okay, so the storage volume released from storage for total volume per change in H. That's what we got. We multiply that times B, we get specific storage. Here's how it works. VT is A times B, so the B's cancel. Okay, so specific storage is a property of the material. We multiply the property of the material times the thickness of a layer. We get the property of the layer. So this is a property of material. It's the like weighted compressibility. we multiply by B, we get a property of the layer. So that's the way the storage properties work. For hydraulic conductivity for the transmission, we have hydraulic conductivity, which is a property of the material and the fluid. But it's like a local property of the stuff there. We multiply by B and we get a property of the layer, which is the transmittivity. Okay, so both transmission, those are kind of two analogs where you have material property and a layer property. Okay, so here's some typical values for specific storage. So water, we said water had a small compressibility. So here it is. Compressibility of water, 1.32 times 10 to the minus 6 per foot. So of drawdown. This is compressibility in units of head. So about 1 part per million per drop in head. Fractured rock is about equivalent to water. Sand and gravel is about 10 times greater compressibility. Sand and gravel about 10 times more compressible than water. And clay is about 100 times. And intact rock is about 1/10 water. Okay, so those are the values for sand and gravel. So if you have a sand aquifer that is 100 feet thick, what's the storativity? So these are handy to, this is handy to know because the storativity you can get just by multiplying a 100-foot thick layer of sand and gravel of this stuff. It's that times 100, which is about 10 to the minus 3. So here's a simple example. A cubic foot of sand aquifer, much water is released from storage if the head drops by 1 foot. So we said that the specific storage was the sand was 10 to the minus 5. So if we've got it 10 to the minus 5 volume per 1 foot drop in head. So if you've got sand, that a cubic foot of sand, and you drop the head by 1 foot, you get 10 to the minus 5 cubic feet of water released through storage. So a small amount, but you need, and so basically you need large areas to be effective. So let me just say, give me 1 more minute. This has kind of an interesting aspect. So if you change pressure in an aquifer by a small amount, then it shrinks and it can rebound. But if you change it by a lot, then it shrinks and it never comes back. So when aquifers shrink, the land subsides. And so here's an example from Central California. In 1925, the elevation was here. And then in 1955, it had subsided to here. And in 1977, it had subsided to here. As a result of pumping these aquifers in Central California for water supply.
Wait, so like the physical ground went down?
The physical ground dropped, yeah. Yep. Here are areas experiencing subsidence. What happens when the ground goes down is it cracks. So there are cracks that form. If you want to have water flowing, I mean, in California, they have water, they move water around in aqueducts. If you've got an aqueduct in cross section, you know, the water's flowing like this. If you have an area where it subsides and does like that, then aqueduct doesn't work. So in California, they've had many billions of dollars of damage as a result of this subsidence problem. And it's a result of the process that we've talked about, where you change the pressure, you increase the effective stress, and that causes the aquifer to deform. Okay, that's a good place to stop.